100%. I'm Matthew. I'm an intern on the BigQuery Data Frames team at Google. Well, I guess intern for the next hour. Today's my last day. But today I'll be telling everybody about my experience contributing to BigQuery Data Frames. First of all, I don't know if you guys all went to my colleague for now, Tim, his talk on Wednesday, but BigQuery Data Frames is basically a pandas-like Python API that you can use to access Google Cloud without writing any SQL yourself. And we're an open source project. The problem with BigQuery Data Frames is that we still need to have SQL to use BigQuery and to leverage a query engine that we built. So basically what BigFrames is under the hood is we create an expression tree to represent the data frames with like BigFrames and everything. So we have two expression trees. We have a BigFrames expression tree and we have an IBIS expression tree. I think the IBIS folks are here today right now, so that's fun. Basically, when you manipulate your data frame, you perform operations on the expression tree. You can like add a node, perform operations on nodes, or like a single node. And all operations are pushed back and only executed when the data needs to be materialized. What this means is basically you could have a data frame that initially starts off with like 1 terabyte of data, and every single time you perform an operation, you don't actually query that amount of data until you get down to say, okay, I want to see the top like 5 rows in this data frame, and only then would you execute your query, and all those operations would be run. This means that the data frames stay as abstract expression trees until the user asks for the data, and the way we end up generating the SQL is we end up compiling our BigFrames expression tree into an IBIS expression tree, and then we compile that IBIS expression tree into SQL. So one example to kind of show how this all works from the development perspective is one thing I worked on over my internship, which is how to recover an exploited struct column. Basically, what exploiting a struct is you have a series of structs, and that's like nested data, and you can convert that into a data frame by exploiting that. Basically, what this task was about was kind of creating a series of structs from a data frame, so kind of like unexploding your data frame. And over here, I just added a little example of what kind of explode does, in case I didn't explain that all too well. And basically what that involved from a development perspective was firstly defining a struct operation to act on n nodes, and basically an n-ary operator. And the reason why we do that is because we can have like an arbitrary amount of columns in our data frame that we're going to turn into our struct column. As a result, we kind of want to be able to kind of pass in an arbitrary amount of nodes into our operation. And generally the mapping is like 1 node for each column. And then we have to define this operations IBIS implementation that will be used to basically end up compiling the expression tree into the SQL, which is obviously very important. And lastly, we have to tie everything together at a data frame level. So basically what ended up happening was we kind of went through the whole development process. I kind of, like Tim helped review and everything. We ended up pushing this to our API about like, I think a month ago. And so that's kind of just my very quick talk of my experience working on BigQuery Data Frames. I've had a great time with the team. I kind of would highly recommend everyone to at least take a look. I had no idea that we could kind of like programmatically generate SQL in such like a reliable, consistent way. And I think everyone on the BigQuery Data Frames team is like super motivated, super talented, and I think it's been a great experience. So yeah, thank you everyone.
Thank you. It was my first PyData, and someone from NVIDIA yesterday said, why don't you give a lightning talk? So it's going to be something different. So my name is Rachel Girard, and you can find me on LinkedIn right there. So I'm working on 2 startups. I'm talking about one. I used to be head of ML at Hearst, a large media company. Before that, Greenplum, but my dark side was Wall Street for many years. So I got interested in jewelry design, and a lot of what I saw was like flowers and ocean things, and like things that, as a New Yorker, didn't like resonate. And so these are the things that like I grew up with in the city, New York Yankees, the Beatles, so forth. And then I studied math, and so I love surfaces. So I had this idea of making typeface for like in 3D for jewelry. And so how do you think about 3D in terms of type? You could extrude it, you could bend it, and it's super ugly. And so how do you inspired the third dimension, the Z, from the first two. So this is a typeface by Cassandra, Art Deco, 1929. And so I thought, how do I take that and make it a 3D model? And so these are my versions of it. And so all these are made in Rhino, using Grasshopper with algorithmic tools and so I thought, okay, like this is so beautiful, everybody liked it, but I looked at it and I'm like, it's not really innovative. It is like extrusions, it's surface coloring, and maybe there's like a 3D element to it. And this was like the process of taking the type, the Bezier curves, putting them into Rhino, and then using Grasshopper. But is it like an extrusion? Am I creative? So I asked Ali, and I said, could you come up with like 2D type? So these are the things that it came up with, A, B, C, D. And some of them were successful, like the G. H, like it's really inventive, like the thing is behind itself. The I is like infinity. So really, like a lot of creativity, that's supposed to be an M. N, that does not look like an O, but some of it was really successful. And so I said, okay, great. So I have all these gorgeous looking things, but they're JPEGs and not 3D models. So how do I go to a 3D model? Or how do I just make a typeface from it? So that's like one way of like, how do I reflect it down? And so I created a path where I have the JPEGs, I look at depth estimation from these fake images, and using edge protection, masking, and create the 3D model. So I do this in Rhino, generate the point cloud, shrink wrap it, and then create the mesh. So how do I do 3D to 2D? How do I do 2D to 3D? How can I take a JPEG and then make it a 3D sculpture? That's it. Thank you.
Thank you so much. Hi, okay, perfect. I just made some software, and I put it on GitHub, and it's now your favorite piece of software. You've been using it loads, you've been writing a bunch of stuff with this piece of software. And the latest version is 2.4.8. And I've done some stuff, and I'm putting out a new version. And I've just released 2.5.0. How do you feel about that?
I'm excited.
Good. Excited is good. Can you just adopt this? Can you just move your code to this? Yeah? Sure? This is a PyData library. This is part of our community. Do you trust it? I don't trust it. Okay? People are used to semantic versioning, a way of versioning where you say, if I change the big number, I'm going to break stuff. If I change the middle number, I've added kind of an orthogonal feature to what you're doing. And if I change the little number, I've just fixed a bug. How many times have you seen a release recently that just does one of those things? Right? They're rare. Unless you use a hypothesis, which releases for every single commit every time, which is great. Okay, so there's a great law that kind of talks about the fact that you go and fix a bug in your piece of software, you're probably going to break someone's workflow somewhere because they probably depend on that functionality. Right, and there's this law about any observable behavior in a piece of software will eventually be relied on by someone. And so if you fix a bug, and there's a great XKCD about this. So understandably, people are cautious about semantic versioning. And I think within our community, within the PyData community, we kind of loosely follow this as a general practice. It's like, oh yeah, it's great in theory, but in practice, it's hard. But people that don't like semantic versioning start doing this. Right? I've done this in projects. So I just released a new piece of software. I switched over to calendar versioning, right? Same project, we still love it, we're still writing loads of code with it. We're now on 2024.7.8, that is a version. And I'm going to make a new release now. I'm going to say 2024.8.0 because it's a new month. We have a new version. Are you excited about this one? Do you trust this one? Can you adopt this one? Yeah. The calendar versioning also has exciting challenges. And I think for something that's like a distribution, if you're an operating system, or if you're a collection of configuration, or if you're a model that's been packaged up in some way, like dates make sense, right? But it doesn't necessarily make sense for software where you're trying to communicate things to people, because there is very, very little information in this, other than the day I hit a button. And the worst thing is if you have lots of software that all works together, and they kind of get released roughly around the same time, people start adding semantics to this that don't exist. And you go, oh, okay, well there's these few libraries, so I'll just use versions that are all on the same month, the same day, kind of roughly. These all work together, right? But it's like, well, this one depends on that one, and that one depends on that one, and this one didn't support the new version until like 2 months later. So you need like, you know, the October one of this to go with the August one of this. Calendar versioning is a nightmare. And yeah, I went to a conference and I tweeted out this meme, just trying to be clever. But Wolf, who works on Pixie and Mamba and a bunch of stuff, put this in one of his talks, kind of talking about these challenges around these things. And I ended up writing a blog post where I was kind of talking about, so I work a lot in Dask, and we've moved to calendar versioning in Dask, and I've had all sorts of headaches and challenges and problems within Dask. And so I kind of thought, well, is there another way? Can we do something different? We kind of don't like semantic versioning, and we kind of don't like calendar versioning. Is there something else? Well, we kind of already do something differently in our community. We don't quite do semantic versioning. It looks a bit like it, but it doesn't really have a name. So can I write another ranty blog post and give this thing a name? So I wrote a blog post titled FBER, and ranted on the internet about we should do this differently. And you jump forward a few months, and now it's used by like a bunch of great projects. So like, hooray, you can influence people with blog posts. FBER kind of just outlines what we generally do. Instead of trying to say, this is a bug fix, this is a feature, this is a breaking change, we just try to say, this is small and it shouldn't affect you, this is medium, you might want to test it, and this is big, you know, hold on to your hats, you need to do some work. So like, I go and read the blog post, basically. Like, it's got a bunch of stuff about how to do FBER, which is basically the same as SEMVER. You don't really need to do anything different if you're already doing SEMVER, and you're probably already doing this, and a bunch of projects are already doing this, and now they've added a nice little badge to their README to say, oh yeah, we're doing this thing, you know what to expect. So now, if I release this, you have a bit more context, right? I can kind of cautiously adopt this. I know in FBER I can cautiously adopt this. So I think I'm at time. Thank you. And go read the blog post. Also, I have stickers, so everyone likes stickers.
Hello, everyone. My name is Michael Pilsov. I'm here to present to you an art project, basically, and it's very much related to data. I am an artist. I'm a mathematician. I really like color, and it always has intrigued me. I also like machine learning, and I want to know how machines learn. I want to visualize things. So there is basically a rainbow. It's all of the, not all of the colors, a lot of the colors put around a circle. So it's a one-dimensional thing which is wrapped around. This is ordered by hue. So colors that are close together are next to each other, right? Reds are next to reds, yellows are next to that. And I want to know, could a machine figure this out on its own? But not only just of all of the colors that we could sample, I wanted to look at colors that we actually use in our day-to-day language. So here's the XKCD color survey. There's 949 colors in there, and humans labeled them. So these are the colors that we find useful in our language. There's a lot more greens than yellows or blues. Things like that are showing up here. It's not a uniform sampling of space. When you go through this in hue order, that's what that little path is tracing out. So you're seeing that it's going through a cube and putting things in order. Well, this is a three-dimensional space. Order is kind of hard to look at here, isn't it? So I want to know, how do we go from 3 dimensions to 1 dimension? Try a couple different ways of doing that and see what happens. So here's a control. I used a embedding algorithm, UMAP, to do some dimension reduction. Kind of a weird result. Like, yeah, the colors are close to each other, but I wouldn't say this is a good order. Here's an example of using a supervised machine learning algorithm. So tell it what the actual hues are and have it learn the 3-dimensional to 1-dimensional mapping. That seems to work okay. Most of the time it can learn this, but that's not the question I was interested in. I really want to know, could it discover this on its own, simply being told to keep close colors together? Before I move on, I will comment that notice it's unstable. This is something very interesting to me. Like, where you stop your training process will change order, which is odd. It's not how humans perceive things or think about things. Here's another example of supervised. It sort of takes a little longer to come to a good solution, but eventually sorts the colors out. And And there you go, starting to get closer. Unsupervised, on the other hand, not so good. It does put colors close together, but it really matters how you define that objective function. What does it mean for close colors to stay together? And so I just did this a lot. I threw a lot of compute at this, like hundreds of thousands of attempts. So on the left here, on that side, is all of the supervised attempts that I've collected. There's 100 of them here, and put into a grid. On the other side is the control, that like embedding algorithm, UMAP. Obviously not so great, but the learned one, okay. Unsupervised, we can see some trends, right? There's certain types of choices that are being made, but ultimately, it only kind of sort of hits on the right answer some of the time. And so this just got me thinking a lot about how do machines perceive the world, how do the way that we define the objective functions that we minimize or maximize influence what this machine can learn or discover. And what I did was print all of these out with very high resolution printing. I arranged them all on a wall together in ordering based on a Hilbert curve so that different algorithms wouldn't be right next to each other. So you don't have any two images next to each other from the same algorithm. And I put one image in here that's the actual color wheel. And I asked humans to find it. Kind of. So some people were able to find it. Most, not so much. Sometimes someone will walk up in front of this thing and just spot it immediately. And that to me was like, the machines are not that good at fooling some of us. And I found that very, very interesting. So there's some close-ups of the prints and just a summary of the tooling that I used here. Yeah, this was a fun project, taught me a lot, and needed a lot of compute. And there was a lot to learn about trying to just do this all at once, basically, because I didn't want to wait for 100 images. I wanted to do it in like 2 minutes. So yeah, thanks for listening. You can find out more about the project on this website. And yeah, thank you.
Everyone can see a Jupyter notebook here.
Yeah.
And we've all used pandas, and we know what pandas looks like for tabular display. And now normally we just type df.head, df.describe, maybe do some histograms, and then every time we edit this data frame, we're going to do that again. I made Buckaroo because that's a crappy experience. Here is Buckaroo with the same data frame. So now we can scroll through 5,000 of the 100,000 rows here. We can scroll left, we can scroll right. We have histograms. We have categorical histograms for discrete columns. And we can tab over to summary stats. You can also search. I know, we all know how to do these things with just pandas or polars, but you have to look it up every time, and the syntax is not easy to use. So now we've filtered these city bike trips to just roads where a canal occurs. This is great. This makes your life a lot better when you use data frames, which you probably do very frequently. There are stats here that take time to run, and if you don't run them, you're going to make mistakes. And every time I don't look at the data and do those things, I make mistakes. You can also customize Buckaroo to add analyses. So we'll make another data frame, and now we're going to add a 99th quantile analysis. So we want a summary stat of what the 99th quantile is. And we write a little bit of pandas code here, and then we put it into the view. So now we have the same main view, we have summary stats, and we have this 99th quantile analysis. You can add your own analyses to this and quickly switch between views without typing anything, and you can build your tools to be smarter and work better with you. There's more. Now we can add a post-processing function that does transposition. So I only did 5 columns because you're not really going to do this, but still. Okay, here's the regular data frame, and you toggle over to transpose, and you get the transpose view. And that was 3 or 4 lines of code. And now we can add other ones. So, counts does not work well. We can do error processing, where, what did we decide here? We decided that every value less than 20 is an error, and we highlight that. There's a whole gallery of the styling you can do for Buckaroo. Color maps, histograms. That's it. So give it a try, pip install Buckaroo, and buckaroo.dev will take you to the GitHub page. Thank you.
Everything. Okay, so the widgets project. So I'm Philip. I founded Beaches on AI, a company to support companies, their data and AI strategies and implementation. And I pretty much like the Databricks approach that encourages true ownership of your data and AI. And I mean, coming from Europe, you know, it's very important for companies in Europe not to ship their data outside European borders. Yeah, so in the last couple of months, we were working on visual models for future detection and smart annotation, in particular for cross-domain industrial applications. So while working on this, I had the feeling that we need to have a better understanding of what's going on with the models and have possibilities to also see the results and to play around with it. And that's, yeah, when I came up with this idea of having a more interactive way of seeing the data and working with it. And yeah, so why? I explained that. To support the use of proprietary visual models. How do we do that? I started off with just a widget, but then I felt, okay, this is going to be complicated as soon as the bug gets more sophisticated. So I came across AnyWidget, which is a project by a guy called Trevor Metz. Maybe you've heard of it. It's really cool. It's allowing you to improve the experience with widgets. But still, I wanted to have like a real app experience, kind of experience. So yeah, I thought, okay, why not use a framework? So I used React, and there's also a nice project called React Jetty. And I tried this, and now let's cross our fingers. Let's see if it pops up. And there we go. Doesn't look too spectacular now, but it's also pretty small. Okay, but it's like a fully featured web app, running in your Jupyter notebook. So you're not only able to have your data and your AI inside your VPN or on-prem, but also your software. So you can ship the app to where the data is. So what does this do? Yeah, we can select images. I mean, this is like a real app. So the features that apps have. We can zoom in, zoom out, and do all kinds of fancy stuff. This is bird's nest data that I put up from the internet just to show you how it works. So we can select objects in the images, and everything works. It should just detect the bird's nest, which it does correctly. Yeah, so you have different features in here. You can play around with the point size, play around with the cutoff, which enlarges the mask or makes it smaller. We can show a heat map, or automatically draw a bounding box around the object that you have selected. And yeah, this is really cool because all the data is synchronized with your Python side, so it talks to each other, and you can just annotate a couple of images, export the bounding boxes, and for example, train a model that you can apply in your production process or what you have. Yeah, brush. This is for anomaly detection. Just select what you're interested in. Determine its errors, and then you can learn that. Yeah, I think I showed everything that I wanted to show you. I'm going to publish the code of the app, so if you're curious or interested in developing fully featured apps for Jupyter Notebooks, feel free to check it out. If you're interested in the models, also feel free to come and speak to me. Yeah, thank you. That's it.
Oh, yeah.
Very unfortunate. But someone told me to give a lightning talk. She was like, I don't need anything. And then she backstabbed me by having slides ready. And I was like, are you kidding me? That's crazy. So I would love to talk about things that everyone's interested in, but I don't really know you guys that much. So I'll talk about things that I'm somewhat interested in that have something to do with data. So how many of you people use BigQuery? Surprisingly, a lot of people, considering that I haven't really talked to that many that use BigQuery. So for those who have or know people who do, is cost or performance like a concern to you guys? Probably not performance, it's really fast. Someone does not like the cost of BigQuery. The Google people here will not be unhappy about that because you're still paying for it. But so what I decided to do with data is, what if we could do something like SQL, like BigQuery does, but not necessarily BigQuery. We have Athena, we have Microsoft Fabric. Just learned at this conference from some Microsoft consultant. Yeah, learning a lot of things this conference. I'm not even from the data world. So what if we could just do that but cheaper? And I didn't realize that NVIDIA was going to be such a big deal here, but someone probably talked a lot about Dask over there, and then someone else is doing Spark Rapids. So these are distributed computing things that you can run SQL or PySpark or Python on really big data sets, like 100 terabytes, and you can get GPU acceleration. So a lot of people think that GPU acceleration is just for performance, but if you combine that with serverless, you actually also get it a lot cheaper. Now the question is, do you actually need that? Do you need GPUs to get a little bit more juice or a little bit more juice for your dollar on the cloud? Fortunately, the answer is no, or so Google says. Like if you do Spark, oh, your data engineer is really smart. You get a 3x cost efficiency. But it turns out that if you do that and then you add GPUs, you actually get like a 6x cost efficiency, or so my benchmarks say on Sunday. Yeah, I would love to talk to more people about like big data, because I actually come from distributed computing at Twitter, doing performance and cost efficiency there, but mostly for compilers. So like the big frame guys and the IBIS guys, we're talking about rewrites. Not doing that anymore, mostly just focused on big data stuff. But yeah, would love to talk to people more about GPU compute for their data needs. As for why I'm back in data, so I wasn't in data for a very long time. That was because of efficiency, but not because of compute efficiency. So I was doing physics, and there were a lot of simulations, and this is like before we even got to the ML part. We already had a lot of linear algebra. And since this is PyData, I get to talk about that because I was using a lot of NumPy. So who has used NumPy with multiprocessing? Cool. So about the same amount of people, different people, but about the same as people who've used BigQuery. And you guys probably use multiprocessing because you couldn't wait for your results, right? Yeah, kind of.
I only had a laptop at that point, and they didn't give me access to their supercluster. So I waited 18 hours after making a lot of estimations, and I couldn't play video games on my laptop at the time because I only had 8 cores, and it was a horrible experience. Especially because at the end of those 18 hours, when I was saving the files to disk, right before the file saved, there was one last matrix multiplication, and that's the issue. The matrices didn't multiply because there was a shape error. And that happened multiple times, and I was like, all right, I'm going to compilers so I can stop this from happening in the first 18 seconds of the run instead. Now, I wouldn't even like really think about that as much because I could just run it on CUDA. And instead of wasting 18 hours, it could only waste 2 hours. Yeah, I don't even need to go into compilers. I wish I knew CUDA back, I wish I knew CUDA back in the day, but apparently now we have Python libraries that can do all this stuff with CuPy and whatnot. So definitely, people who are using multi-processing with NumPy, check out CuPy. I think there's a lot of cool stuff there. I will end this weird lightning talk with one last thing about CuPy, which is again another complaint. It is about strings, and it's always something about Unicode or strings or bytes that it's going to bite me in my back end. But I hope that other people are going to contribute to CuPy and make that a reality, so I can use it. Because why would I care about strings and CuPy when I'm talking about data? Maybe some people say labeling. It's not about labeling. It's about using the GPU as a HTTP web server. I was like, one afternoon, wait, there's this thing called UCX and UCP, and it's like TCP, but not really. Can't I just send the HTTP websites like HTML over the GPU and use like RDMA? The answer is yes. But CuPy wasted about like 5 hours of that afternoon because I just didn't deal with strings. Too bad. Please contribute so that I don't have to. That's it.
Thank you once again.